So we know that the matrices are like function, but some functions have inverse function. So in this section, we are going to talk about when does the given matrix have an inverse matrix. And like what it is on the function case, the matrix has inverse if A is 1 to 1 and onto. So recall that 1 to 1 is equivalent to have each columns of A's are linearly independent, and onto is equivalent to the columns of A spans Rm. So let's analyze when does these two conditions can happen for the given matrix. So suppose that you have n by n matrix such that A maps an element in Rn to Rm. So if n is larger than m, can A have an inverse matrix? So in this case, we have more columns than row. So it's like the horizontal shaped matrix, something like this. Well, if you have more columns than row, then we know that n number of vectors in Rm is not linearly independent. And that doesn't satisfy the first condition over here, so it's not 1 to 1. Okay, so then what if n is smaller than m? Then in this case, we have more rows than column, so it's like the horizontal shaped box matrix. Then to span Rm, the condition we need was to have pivot position for each rows, but the best case scenario is something like this. So we have some rows over here that doesn't have pivot positions. So from this observation, to span Rm, we need n should be at least greater than or equals to m. So to satisfy both conditions, we need n should be the same as m, or the number of columns should be the same as the number of rows. And intuitively, the shape of the matrix should look like a square matrix. And in this case, if you RREF the given matrix, then because we need all pivot position for each rows, then we get 1 for diagonal entries, and the rest should be 0. So how do we call these kind of matrices? We call this as the identity matrix. So a square matrix n by n matrix is said to be invertible if there exists an inverse matrix denoted by A inverse such that A inverse times A equals to the identity matrix, or A times A inverse equals to the identity matrix. And a matrix that is not invertible is said to be a singular matrix. So let's check that whether B is the inverse matrix of the given matrix A. So if you multiply these two matrices, AB, then this equals to 2, 5, negative 6, and 6 times 6, negative 5, 6, and 2, which is the same as, I guess 2 times 6 is 12, plus, I guess 30, minus 10, plus 10, and negative 36, plus 36, and 30, plus 12. And this will give you 42, 0, 0, 42. So here, what we can tell is, well, B is not an inverse matrix of A, but if you divide both sides by 42, say like 1 over 42 times B, well, then this is an inverse matrix of A. So we have A times 1 over 42B equals to 1 over 42 times AB, that equals to 1 over 42 times 42, I2 equals to I2. So we have nice formula for inverse matrix when the given matrix is 2 by 2 matrix. So suppose that you have 2 by 2 matrix such that AD minus BC is not equal to 0, then we have A invertible and its inverse matrix is given by this. And the reason why we need this condition is that we have to divide by this quantity over here. And if AD minus BC equals to 0, then we call either A is not invertible or it is singular. So because we can determine whether the given matrix is invertible by using this quantity, so we call this as a determinant of A, or we simply denote this by determinant of A. Then 2 by 2 matrix is invertible if and only if the determinant is not equal to 0. And let's pause the video and try out the inverse matrix of the given matrices if the inverse exists. Okay, so let's solve these problems together. So here, AD minus BC equals to 2 times negative 2 minus negative 5 times 1, which will give you negative 4 plus 5, that equals to 1. So the first matrix is invertible, and the inverse matrix is given by 1 over 1. So you switch the diagonal entries, and you put minus signs on the off-diagonal entries. So you get 5 and negative 1 over here. So the inverse matrix should be negative 2, 5, and negative 1 and 2. Okay, for the second matrix, well, if we calculate the determinant of A, then it is defined as AD minus BC, which is 12 minus negative 3 times negative 4, which will give you 12 minus 12, which is 0. So we can conclude that the inverse matrix does not exist. So basically, we can solve the system of equation by using the inverse matrix. So if you write the system of equation as AX equals to B, then if you multiply by the inverse matrix of A for the both sides, then this gives you A inverse times AX equals to A inverse times B, or you get IX equals to A inverse B, or we get the vector X equals to A inverse times the vector B. So let's pause the video again and try to find the solution set of the given system of equation using the theorem above. Okay, if you write this as matrix equation AX equals to B, then we have A as the coefficient matrix, which is given by 1, 3, negative 4, negative 5, and X equals to x1, x2, and B is negative 7 and 7. And we can calculate the inverse matrix of A. So here the determinant of A is given by AD minus BC. So it should be negative 5 minus 3 times negative 4, which equals to negative 5 minus negative 12. That gives you 7. So A inverse equals to 1 over 7. So you switch the diagonal entries. So you get negative 5 and 1. And you put negative signs to the off-diagonal entries. So you get negative 3 and 4. So if you plug this and that one to this equation, then we get the vector X equals to A inverse times B, which is the same as 1/7, negative 5, negative 3, 4, and 1, and 7, 7. And if you cancel out 7 into entries of B, then that gives you negative 5, negative 3, 4, 1 times negative 1 and 1. And this is the same as 5 minus 3, negative 4 plus 1. And this gives you 2 and negative 3. So you can conclude that x1 equals to 2 and x2 equals to negative 3. Okay, so there are several properties of inverse matrix. So if you take the inverse and then inverse again, then you will restore the same matrix. So the A inverse is the same as A. And the inverse matrix of the product of two different matrices is, well, similar to the transpose matrix. We get B inverse times A inverse. And you can switch the order of transpose and taking inverse. So which means A transpose inverse is same as A inverse, and then take transpose. So if the product of n by n invertible matrices is invertible, then its inverse is the product, but you have to write in the reversed order. Elementary matrices are matrices that you can get from taking the elementary row operation on an identity matrix I sub n. So let's say I3 to be an identity matrix on 3 by 3 matrix. Then we can obtain E sub 1 by adding 2 times row 2 into row 3. And E2 is simply like switching the first and the second row. And E3 is dilating the first row. We call these kind of matrices as the elementary matrices. And this is because we can perform row operations by multiplying these elementary matrices. So for example, so if you multiply E2 into arbitrary 3 by 3 matrix, so let's say you're multiplying this into A, B, C, D, E, F, and G, H, I, then the resulting matrix is D, E, F, A, B, C, and G, H, I. And note that the first and the second row are switched each other. So multiplying elementary matrices exactly do what you did on the identity matrix. So here are some facts about the elementary matrices. So basically, we can invert the ERO process. So elementary matrices are invertible. And the inverse of elementary matrices corresponds to the row operation that transform E back into the identity matrix. And the theorem states that the given square matrix is invertible if and only if A is row equivalent to the identity matrix, and furthermore, all the row operations you do to reduce A to I also transforms your identity matrix into the inverse matrix. And this gives us an algorithm for finding the inverse matrix A inverse. So to keep track of all the row operations, so the first thing you do is to take the augmented matrix using A and I. And if A is row equivalent to I, then we can reduce this matrix into the identity matrix here. So what you get on the right should be the inverse matrix. And if A is not row equivalent to I, then A does not have an inverse. So let's practice the given algorithm to find the inverse matrix of the given matrix. So the first step you do is you build the augmented matrix using A on the left, and then the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 on the right. And then the second step is to RREF the given augmented matrix. So let's pause the video and try to find the RREF of this augmented matrix. Okay, so have you reduced the given matrix? Well, let's do this together. The first thing that comes to my mind is I just add R1 into 6 times R3 to replace R1, and R2 plus 3 times R3, and then replace R2. Then this gives you 1, 2, negative 3, 0, negative 1, and 2, negative 2, 0, negative 1. And then you also have to keep track of this operation in the right side as well. So you get 106, 0, 13, 0, 0, 1. And then R3 plus 2 times R1 gives you 1, 2, negative 3, 106, 0, negative 12, 0, 13, and 0, 4, negative 7, 2, 0, 13. Okay, now if I add R1 plus 2R2 and replace this to R1, and if you add 4R2 into R3, and then replace this to R3, then you get 101, 1 to 12, 0, negative 12, 0, 13, and 0, 0, 1, 2, 4, and 25. And then if you subtract R3 from R1 and 2R3 from R2, then this will give you 1, 0, 0, 0, negative 1, 0, and 0, 0, 1. On the right side, we get negative 1, negative 2, negative 13, negative 4, negative 7, negative 47, 2, 4, and 25. And if you reverse the sign on the second row, then this gives you identity matrix on the left and the inverse matrix of A on the right side. So you can tell that A has an inverse matrix, and A inverse is given by negative 1, negative 2, negative 13, 4, 7, 47, and 2, 4, and 25. So we can generalize this trick to n number of linear system of equations. So suppose that you have n variables like a11 times x1 plus a12 x2 plus and so on until a1n xn equals to b1. And you have all the way the equation, n number of equations, and the last one is an1 x1 plus and so on, plus a and n, xn equals to bn, then we can certainly form the coefficients matrix using a sub ij's. So we form a equals to a sub ij, and x equals to x1 through xn, and the vector b equals to b1 through bn. Then we can form the matrix equation given by ax equals to b. And once you can find the inverse matrix, then if you multiply the inverse matrix to the both sides, then this will give you x equals to a inverse b. And this way we can find the solution for the given system of equations.